Welcome to the week 3 Teaching with Data cohort for Data Classroom. Today we're going to take a look at graphing using time as one of our variables because time can be a little bit tricky. There's also different ways we can handle it, whether we want to treat it as a numeric or a categorical variable. For today's demo, we're going to be taking a look at our epidemic and a pandemic data set. This activity takes a look at Kentucky emergency medical services data from about early to middle of 2020. Public health officials were understandably concerned about how stay-at-home orders to enforce social distancing were going to affect opioid addiction treatment. Typically, that treatment's administered face-to-face, and so their hypothesis was when people were seeking treatment were no longer able to meet face-to-face, there might be an increase in opioid overdoses. And so in order to investigate this, they took a look at the number of daily EMS runs with refusal. That's when somebody who's picked up by emergency medical services tells the responders that they don't want to go to the hospital. And that's usually a pretty reliable proxy for individuals who overdosed on drugs. And so they've taken a look at the number of EMS runs with refusal before and after stay-at-home measures were put in place in Kentucky. So with that context, let's get started and talk about time as a variable. So you can see in this column, we're looking at dates from January 14th. It goes through, I'm going to say late spring. Yeah, looks like it goes through April. And one of the problems with inputting time as a variable is that it violates tidy data, right? So one of the first rule with tidy data format is that each variable gets its own column. And the way we've recorded time here actually has 3 variables, right? It's January 14th, 2020. That's a month, a date, and a year. And so graphing software can't really handle dates like this. We have to do a little bit of a transform. I'm going to take a moment to demonstrate how we did that in Google Sheets. If you feel pretty comfortable in Excel and Sheets, feel free to skip the next segment of this variable. But to show what we had to do in order to get it in tidy format, I'm going to take us to this Google Sheet real quick. So thankfully, Google Sheets makes it really easy. I'm on a Mac, so Command-Shift, I can select the entire column of data. I'm going to go to Format, and then just change it to a number. So Excel and Sheets have a formula where they're picking a reference point for that date and then basically counting up to the date as you've entered it. You probably don't want to graph 43,844 as the starting point for any kind of measurement of time. So I'm going to change these so that the first day is t equals 1. In order to do that, I'm just going to input a little formula, say A2 minus 43843. And then Google Sheets helps us do the rest. And so now we have time in a tidy format that will work. As you can see, we've done that here to be able to treat time as a numeric variable. And we've also gone ahead and grouped all of these observations, each in their own row, as either being before or after stay-at-home measures were put in place. I think that was March 16th. So all the dates leading up to March 16th are given the categorical variable of before, and everything after that time, given the time after, given the variable after. So that's just an example of 2 ways you can treat time as a variable, either as a numeric or as a categorical. And as we'll see in a moment, that allows you to do different types of analyses when using time. So again, this is kind of an extension of our looking at the art of graphing and trying to really tease out what the data are telling us. So let's go ahead and graph. Let's make time our x variable and daily EMS runs our y variable. So you can see there's clearly some kind of data here, but it's not really clear what the pattern is. There's a little bit of overlap, so we're calling what we can do with spacing, with color to tell a bit more of a story here. I'm going to go ahead and add the before and after and make that the z variable, so we can group them by z. Additionally, in order to help visually separate these 2 groups, we can go ahead and throw in an x-axis reference line by going to Appearance. And I'm going to put it, having done this before, I know that March 16th comes out to be 67. And so again, right away now, instead of fixating on what looks like it might even be some sort of sinusoidal curve or some sort of seasonality, you can kind of see that there is a difference between these 2 groups. And taking that a step further, we can, since we're treating time as a numeric, we can add a regression line. And of course, we want to group by z to see the difference in the two populations. And the slopes aren't all that different, but we're not really concerned about slope. We're more concerned about the intercept here because we're looking at before and after. And it does look like, as a result of stay-at-home measures, there seems as if there was an increase in the number of EMS runs. Now, if we really wanted to prove that with a more conventional analysis, we could use a t-test. That's going to require us treating time as a categorical variable. But thankfully, that's really easy to do using Data Classroom. So if we change the before and after, right, those are our two groups, the means of which we're going to be comparing in a t-test. We can see, okay, it looks like there might be a statistically significant difference between these two means. But one of the assumptions inherent in a t-test is that you're sampling from distributions that are at least approximately normal. And the good news is, again, that we can do that using Data Classroom. So before doing a graph-driven t-test to see if the means are significantly different, let's take a look at the distribution of these two samples to see if they're approximately normal. So I've gone ahead and made the daily EMS runs with refusal, our x variable, and then grouped them by z, again over here, so we can take a look at the two populations we're sampling from. And so the red group is after, and that looks approximately normal. You can see there does appear to be a grouping around a mean. And the same can roughly be said for gray. We don't see a significant skew in either direction, though they're relatively small samples. They do at least both look approximately normal. So I would go ahead and sign off on this as being good proof that it was appropriate to run a t-test. So let's go back to our scatter plot, group them before and after, and go ahead and run a graph-driven t-test. And you can see that Data Classroom's gone ahead and selected the appropriate test. We have categorical variables at the time. Again, if we had selected this option while we were still treating time as a numeric variable, it would have recommended linear regression because we were dealing with a numeric variable here. Let's go ahead and take a quick look at whether or not the p-value is below our threshold to reject the null, but these do have the same mean. And there you have it, p-value below 0.01. That's typically the threshold we use to be able to reject a null hypothesis that the two groups have the same mean. And there you have it. Quick way to analyze time, both as a numeric and categorical variable. And they both give you different insights. One drawback of the current view is that you don't get a sense of the length of the study, kind of the range of the dates over which the data was collected, but you do more immediately see, okay, it looks like the means of these two groups are significantly different. Thanks for joining us. Check out the rest of our videos on YouTube. As always, feel free to reach out to me, Blake at dataclassroom.com or info@dataclassroom.com if you just have a more general question. Thanks for stopping by.